learning in medical imaging, theory, use cases, and implementation. And very briefly, my name is Brani Rusanov. I'm a first-year PhD student down at Sir Charles Gairdner Hospital, and my project involves developing an artificial intelligence pipeline for adaptive radiotherapy. So a quick overview of what AI is. I think the words machine learning, AI, and deep learning get thrown around quite a lot, but not many people, they use them interchangeably, but people don't really understand specifically what they mean. So artificial intelligence is an umbrella term that encompasses machine learning and deep learning. And specifically, machine learning is a subset of AI, which features a family of algorithms that find the optimal solution to separate data, and that's a classification, or the best fit to the data, and that's a regression problem, without being explicitly programmed to do so. Whereas deep learning is the same thing, a classification or regression model, except it's performed using artificial neural networks, which is a big part of what I'll be talking about today. And finally, we have Skynet as the final iteration of artificial intelligence. So I want to try and conceptualize artificial neural networks. I'm just trying to minimize this. It's a bit annoying. Yeah, okay. So again, what are we trying to do with our artificial neural networks? Well, we try to form a decision boundary between data points to classify or find the best fit to data in a regression problem. Classical machine learning algorithms like linear regression or logistical regression, as Jake described in his presentation, aim to find the best parameters in a template equation. And this equation may be one that we're all familiar with y equals mx plus c. So we try to find m for our x data points that best fit to that data and try to separate that data. But sometimes our data is too complex to be linearly separated. So what can we do? Well, we transform our data to make it linearly separable. And artificial neural networks, in essence, transform our input data using many nonlinear operators called neurons in order to make it more easily separable. And visually, in the bottom diagram, we see how a data set may be augmented or transformed in order to make it more easily separable between the two classes. So this is kind of the anatomy of an artificial neural network. It consists of our input layers at the beginning here, and our inputs may be features such as weight or age or other clinical variables, or they may be manually extracted radiomics features as summarized by Nathaniel in his presentation. And these features, as he noted, may number up to in the thousands. So you can imagine the data set is highly multidimensional, and finding relationships within that data set is very difficult. And this is where deep neural networks come into play, because they are highly specialized in working with large data sets. So as we input our data into the input layers, they move through into the hidden layers. Now the hidden layers perform nonlinear operations on those data points. And deep learning gets its name from the stacking of many such hidden layers. And very briefly, without getting too mathematical, what a single neuron does to manipulate the data is that it accepts every single data point that is fed into it, and then it multiplies that data point by a learnable weight parameter. And every single input has a unique weight associated to it as it is fed into that particular neuron. Then these results are added together and sent through to the next nonlinear operator or neuron. And this occurs through many hidden layers until we get to our output. And our output should resemble something like this in feature space, where the data is now linearly separable. And the predicted output can be classes, for example, the tumor grade that we're analyzing based on our extracted radiomics features, or real values, for example, the estimated time of survival for a particular patient based on the characteristics fed into the model. So what are some of the use cases of artificial neural networks in medicine? Well, one famous example is arrhythmia detection. So a wearable band was developed that maps sequences of ECG samples to rhythm classes. And it was found that the model could outperform the average cardiologist in sensitivity and recall, as seen on the right-hand figure. Furthermore, this is a bit of a plug. Jake, Nathaniel, and myself participated in a hackathon recently, and we were tasked to develop a end-of-life prognosis model. So we were assigned 400,000 data points, and we developed 18 highly curated features in order to predict with quite high certainty the likelihood of a patient, whether they should be recommended for palliative care or not, for the last 12 months of their life. And These are just some examples of what can be done with artificial neural networks. So in terms of implementation, for artificial neural networks, in terms of deep learning, not using imaging data, just using tabulated data, we would require software. Well, we only require software. We could probably run these models on our everyday home PCs without the requirements of very expensive hardware. So as Jake mentioned, Anaconda is a great place to start. So Anaconda is a distribution of Python, which includes all of the basic data science packages in a single bundle. It makes updating them and keeping track of them very simple and easy. It comes with a graphical user interface, so you don't have to use any command line inputs in order to initialize all your packages, which is very handy for beginners. Secondly, you'd want your deep learning libraries. So the two most famous ones are Keras and PyTorch. Keras is owned by Google, I believe, and it has merged with TensorFlow. So it uses the TensorFlow equations, and Keras is kind of a high-level library that is very easy to implement, almost reads like a story when you see it in code. Not exactly, but it's very user-friendly. Whereas PyTorch, this has been developed by Facebook. It's more used for cutting-edge research-level projects, and you have a lot more fine control of your deep learning models compared to Keras. And finally, you're going to need a Python IDE or integrated development environment. So the three most famous or most used ones are PyCharm, Spider, and Jupyter Notebook. With PyCharm and Spider, their layout is kind of a typical scripting interface. You don't really get many fancy functions, but it's mainly used for model deployment. On the other hand, Jupyter Notebook functions more like a scientific notebook where you have interactive code cells mixed with multimedia cells or text cells. And this makes it very easy to kind of keep track of projects, keep track of research that you may be conducting, and save different states of the model in a single notebook. And then once you're happy with the given model development, you can then deploy it onto Spider or PyCharm. So I want to run through a very quick practical example of how to implement an artificial neural network in Keras. This has been simplified as much as possible. So first, you'd open up your favorite IDE and import the Keras libraries. So we would import Keras, and then from Keras, we would import the classes we would need. So for this particular example, we would import the models class and also the dense class, which we'd be using to build our artificial neural network. In this example, our data set is composed of 1,000 patient instances, some recommended for palliative care and some not. Each patient has 30 clinical features associated. So that means age, disease type, etc. And we would use these to predict a binary outcome, whether they're recommended for palliative care or no. So a 0 or a 1. We would split our data into training, validation, and testing. I'm going with a 60-20-20 ratio split. And we would store our input features in the X variable and our labels in the Y variable. So the labels are what we're trying to predict, and the inputs are the features that we're feeding into the model. So as you can see, we have 600 patient instances, each with 30 features in our training data set, and our corresponding labels. We have 600, which correspond to every single patient, whether yes or no they're recommended for palliative care. Then we have the same sized validation and testing sets, which I'll describe their function next. So now we move on to building our model. Again, when I said that it kind of reads like a book, we simply define our model and we call it a sequential. This tells Python that we'll be implementing an artificial neural network with stacked layers. This is a universal command to initiate an ANN. Then we simply add an input layer. So looking at the diagram here on the top right, our input layer is initialized by calling input with a shape of 30, meaning it accepts 30 features that we have in our data set. Then we add a hidden layer that I described earlier that performs the nonlinear operations. This particular one has 32 neurons in it. So the data gets sent to 32 different neurons, which perform nonlinear operations. And then finally, we define our final output layer. It doesn't have a special name in this case, but we set it to have 2 neurons because each neuron would then output a probability of whether it it would output a probability for yes, the patient should get palliative care, and a probability of no, the patient shouldn't get palliative care. And that both of those probabilities would add to 1. Moving on, to train our model, we have to specify how we're going to train it. So we first compile it using the Atom optimizer. This is very mathematically heavy, but the literature ubiquitously uses the Atom optimizer for training any kind of neural network. We set our specific kind of loss, in this case, categorical cross entropy, and we use the metric which Jake said never to use, but for example's sake, accuracy is very easy to comprehend and understand. And finally, we train the model using the fit function. So we define that we're using X trained, Y trained, our training data. We set epochs equals to 10. That means that the model sees every data point 10 times. It iterates through the data point, through our data 10 times. And then we specify that we want to use a validation set, and we specify the validation set that we previously generated. And then we may get a training curve that looks something like this. So on the Y-axis, we have the accuracy of the model. And on the X-axis, we have how many times the epoch, which is how many times the data has been looked at by the model. So what we can notice immediately is that on the training data, our model improves indefinitely. However, on our validation data, which the model doesn't use to optimize its weights, it starts off well, but begins to plateau. And as training continues for longer, it actually ends up getting worse. Now, the reason for this is very important to understand for building deep learning models. So you want the model that performs the best on the validation set and not the best on your training set. And this essentially prevents overfitting on your training set. So your training set may have certain characteristics which aren't represented in the real population of your data. And in order to capture as much of the real characteristics of the real data as possible while omitting the training that set specific characteristics, we use the validation set as an external kind of testing set, but not the real testing set, to then use the model that performs best on that validation set. And then finally, we have our testing set, which is again an independent set separate from our validation, but we use it to get the final kind of performance of the model. And in this case, it performed very well, but 98% accuracy, but as Jake would say, that's probably too good to be true. So what are some drawbacks of using artificial neural networks or deep learning models in general? Well, there's the lack of interpretability. So statistical models such as linear regression can tell us which features are important for making predictions, and we can trace that logic that is used by the model. And then we can tell if it's doing something stupid or not by simply seeing how it performs internally. However, unlike machine learning approaches, deep learning models act as a black box. So the potentially millions or billions of learnable parameters that contribute to making a prediction cannot be feasibly tracked or tested. And this makes their predictions untraceable by humans. And this lack of interpretability is an obstacle for clinical implementation, since clinicians are unable to explain the results and apply their intuition to why these results were generated. And a further issue is that legislation is actually requiring patients, or legislation states that patients actually have a right to an explanation of how an algorithm made its choice, which is another hurdle for implementing these deep learning models. But on the other hand, we know from experience that the less interpretable the model is, the greater its predictive capacity. So we kind of have to find that balance or just add greater levels of validation to our models in order to truly harness the power of deep learning without getting tricked by their outputs. So what are some things to look out for? Well, if we have a lack of training data, then we fail to capture the underlying patterns of the data that we're trying to predict on. So as we can see from this GIF, obviously the more data we have, we can tell how that data structure is represented. Furthermore, if the data is non-representative, if our training data is non-representative, then it will not reflect the real population statistics and our model will not perform well. As Jake said, no matter what you do, the data is the most important part of any machine learning operations. So you want to ensure that your training data matches the real population data as best as possible. You may also have irrelevant features. So it's known that with an increased number of features, you need exponentially more data in order to cover all possible combinations of that data. But also data is expensive to get and sometimes not easy, especially in the medical field. So what we can do is remove irrelevant features by taking features that are highly correlated or non-predictive, removing them from our data using feature selection methods. These are very mathematically heavy, but I'm just stating them here for information's sake. Furthermore, we may overfit on our data. So as previously noted, every data set has inherent noise, and overfitting occurs when the model fits too strongly to this noise. Things we can do to alleviate this is we can get more data to reduce the impact of that noise and increase our signal strength. We can use a less complex model that's incapable of modeling the noise to such an extent. We can train for less time. This allows the model to not fit to those very extreme data points which aren't representative of the true population, or we can smooth our data to reduce the impact of noise. Similarly, we may underfit. Now, this occurs when the model is too simple to understand the base structure of our data. And what we can do to overcome underfitting is increase the model complexity. We can train for longer, or we can use feature engineering techniques such as handcrafting more powerful features by combining or transforming them. Now I want to move on to convolutional neural networks, which work specifically with imaging data and not tabulated data, which was kind of what I was just talking about. So a picture is worth 1,000 words, but in this case, it is worth a lot of representation power. So the textures, shapes, and colors contained in images are features which we humans use to perceive and assign meaning to visual phenomena. But convolutional neural networks can extract features, both visual and statistical, which exceed human perceptual capacities. And they do this all by themselves. So how does this happen? I think it's useful to understand how a convolutional neural network is built, and then also how it extracts features from an image. So in this example, we may have an image of a brain as depicted on the left-hand side. And we know that an image is basically a matrix of values, and each value represents a color intensity that corresponds to a real-world phenomena, for example, density in a CT image. And globally, the matrix conveys spatial patterns in relationships, which give meaning to the image. We then have a filter. Now, this filter is a component of the convolutional neural network, and it is also a matrix of values. But however, each value in the filter is learned during the training process. Features are extracted using learned filters through the convolution operations. And very briefly, I want to explain how a convolution operation works. It basically takes a weight value in our filter, multiplies it with the corresponding image pixel value, and it does this for every corresponding filter in image pixel value, sums the result, and places it in the top left-hand quadrant of our convolutional output. This is done for this particular quadrant of the image. In a real training process, the filter would slide across the image. And furthermore, we don't have just one filter, we have potentially tens or hundreds or even thousands of filters that extract different features from our image and store them in a more spatially confined region and represent that output as an abstract representation of our image. And finally, convolutions excel in imaging applications due to their ability to capture spatial relationships. So if we were to flatten this image into a 1D vector and then feed it into an artificial neural network, we're not really learning anything about how neighboring pixels contribute to a given feature, since we're taking every single pixel on its own merit and not how it's and not considering its spatial position vis-a-vis other pixels. And finally, our convolutional output represents features that are compressed in abstract representations of our input. And this is how radiomics features are actually automatically discovered using convolutional neural networks. So based on your minimization task, the neural network will iteratively update in such a way that it will extract the appropriate features to achieve that particular radiomics task. And on the left-hand side here, I've depicted what a filter, a convolution output may look like. It's quite unintelligible to the human eye, but to the network, it contains very important information. And just to briefly cover the learning process, so you would input an image, it would spit out a result. Obviously, this result isn't very good because the model hasn't been trained. We then calculate the error of our model, and we derive a contribution of each parameter to the global error. So we can calculate how wrong every parameter is in giving our output. And then what we would do is we would tweak every parameter in our model in the direction that would minimize the global error. And this would occur for millions or billions of parameters in our convolutional neural network. And this would happen iteratively, hundreds, thousands of times, until the models filter values, extract the features that are meaningful for the specific task. So what are some of the use cases of convolutional neural networks in medicine? Firstly, object detection and classification. So for example, aiding endoscopic examination to identify polyps. Semantic segmentation. So if we have an input medical image, we can then extract a binary map of the particular object we're trying to segment. Deep radiomics. So we can correlate extracted features with patient outcomes, for example, overall survival. Synthetic image generation. So we can create, for example, synthetic CT images from input MRI images, which would facilitate MRI-only treatment planning without the need of exposing a patient to radiation or acquiring a CT image. Or similarly, we can facilitate cone beam CT-based adaptive radiotherapy, so we can improve the image quality of very poor cone beam CTs to that of diagnostic CT images. And finally, we can facilitate optimal dose predictions for radiotherapy treatment planning. So if you just input a CT image of a given patient anatomy, a convolutional neural network can learn from past training examples what the most optimal dose distribution would be for that particular patient anatomy. And in this example, the ground truth is C, DP is the predicted output by the convolutional neural network. And by subtracting the two dose distributions, you see there's almost zero difference. There is some difference, but it's quite small given the challenge of the task. So I want to quickly run over the most popular architecture used in medicine. This happens to be UNet. I'm not sure if some of you are familiar with it or not, but it's been cited by 32,000 people to date. And this is because it's quite a versatile network. It can be used for both classification and regression problems on a per pixel basis. So UNet looks something like this. It is composed of an encoder and a decoder wing. In this particular example, I'm transforming an MRI image into a synthetic CT image. So it would be fed into the network. Convolution operations would be applied. And as we learned previously, a convolution operation shrinks the spatial dimension of the image. So as it travels through the encoder, the spatial X and Y dimensions shrink. However, the feature dimension, which is would be, I guess, 1 in the input image, begins to expand. And this expands because we add more and more filters the deeper we go into the network. So we may have 32 filters in our first layer, 64 in the next, 128 in the bottleneck layer. And this means that we're representing our input image into a smaller spatial dimension, but with a much higher feature dimension. Finally, we want to reconstruct our output synthetic CT. So the decoder wing does the opposite. Now it doesn't use convolution operations, it uses transpose convolutions. These are mathematically tricky to describe, but they essentially expand the spatial dimensions while collapsing the feature dimension to do so. And the use of skip connections are actually what has made UNet kind of revolutionary in this case, because prompts from the encoder wing are sent and added to the decoder, allowing a more accurate final reconstruction of our synthetic CT. So information such as where a bone is near soft tissue better prompts the decoder to reconstruct our synthetic CT image. Or similarly, we can perform the same task for a segmentation problem. So we would have our ground truth segmentation maps for the given input image, and our model would be predicting zeros and ones based on where the output segmentation is. To implement deep learning, convolutional neural networks, we would use the same software packages I previously described. However, we would now be considering hardware. So it's recommended if you're training locally to have minimum 32 gigabytes of RAM, but 128 gigabytes could also be used, and for big machine learning, deep learning tasks is recommended. And finally, you need a pretty heavy duty graphical processing unit. So an NVIDIA Titan can set you back around $7,000. So it's not very cheap. And especially with the COVID shortages and whatnot, it's making it a lot more difficult to get some of these GPUs. Alternatively, though, there are cloud solutions, but as Jake mentioned, ethical considerations must be considered, because you don't want your data to be leaking out or to be violating any agreements that you've made with your given ethical board. So Amazon Web Services allows you to deploy custom models on their own hardware, and they have tools to simplify the training process. And generally, the models train on a pay-as-you-go basis. So you get given some credits, and that allows you to use some allotted GPU power. Similarly, Google has a similar service, but it takes it a step further by predicting the optimal model configuration for your unique problem. So you don't even need to build a model yourself. It kind of analyzes the problem you're trying to solve and outputs a given model that you're trying to use. However, it's not a perfect solution, but it's not a bad place to start for non-experts. And finally, Google Colab is another alternative. Now this functions, it's actually built on Jupyter Notebook, and it's a free solution allowing you to build and train computationally intensive models. However, the free version of Google Colab is prone to timeouts every 12 hours. So you can't train for more than 12 hours without getting disconnected, which is very annoying. And I know this from experience. You can get the paid version, which gives you priority access to hardware, faster GPUs, and no dropouts. But that's still not true, because it still ends up dropping out at even more random times. So in a way, it's even more nefarious. Okay, so what are some considerations for implementations for clinical implementations of deep learning models? Well, we know that deep learning is matching human levels of problem solving and is set to alter the clinical workflow in the coming decade. But the black box nature makes validation and quality control extremely difficult. And so regulatory bodies have a lot of catch up to play. For example, the TGA, as of October 2021, does not mention AI, machine learning, or deep learning anywhere in their regulation of software-based medical systems report. Similarly, the FDA only has a loose AI and machine learning software as a medical device action plan as of September 2021, but no concrete legislation. And finally, in my own experience, my own personal ethics application has been returned to my supervisor, asking him for recommendations for potential reviewers with deep learning expertise in order to advise on the protocol. So it just shows how little expertise there is currently in WA, at least, for kind of regulating and assessing these deep learning projects and models. So what are some more considerations that are suggested people consider when deploying deep learning models? Well, data transparency is on top of the list. So end users should know precisely what data was used to train the model. And this allows limitations of the model to be quantified. For example, in a segmentation model trained on populations with characteristics different from the population it is being used on. So there was a recent example that I heard of that a lung tuberculosis segmentation model trained on the Chinese population was used locally and was found to produce a lot of false positives because there is a much higher incidence of tuberculosis in China. And therefore that model would not be applicable in populations with lower incidence. Furthermore, we must be aware of the changing clinical environment. So any changes to the clinical environment must be monitored and accounted for. For example, new CT imaging acquisition parameters may negatively impact the model performance. And if they're not taken into consideration, this may lead to potentially disastrous patient outcomes. Finally, when we're considering implementing these models in a medical context, a multidisciplinary team of medical and AI domain experts should be formed to evaluate the strengths and limitations of the model. And this should guide users and provide training they should guide users and provide training on using and interpreting the results. For example, they should perform an end-to-end test with the clinical personnel and ensure that all members understand the scope of the given model. And finally, then we must develop a way to perform ongoing quality assurance of these models. So we may perform a statistical similarity check of the new data that we have and want to input into the model with the training data that was used to train that model. And we can then judge if that new data is viable or eligible to be input into the model. Similarly, we can perform a sanity check against another proven method, whether that be manual or automated, and see if the output of our model is agreeing with previously validated methods. Furthermore, we should keep a reference data set that has been made during the commissioning of this model, and then repredict this training set to verify the consistency of the model in case that there has been updates or unaccounted for changes made to the model. And finally, we should collect a log file of suboptimal cases to identify weaknesses in the model and rectify them in the future. Thank you for listening, everyone. Any questions?